Hello. The goal of this video is to show you how we can arrive at the price of a call option through the method of the replicating portfolio. So the main goal is to find a portfolio of assets which replicates the payoff of our option, and for the purposes of this video we'll be exploring it through the scope of the call option. And through the replication portfolio, we will be able to understand how we arrive at the concept of the risk neutral valuation of call options. So we will be looking at the concept through a one-step binomial model. So simply illustrated, we will have at time is equal to 0 our beginning point of our portfolio, and we will have only two possible states of nature: an upward state of nature or a downward state of nature, where the price of our assets would either go up if it's in the upward state of nature, or downwards if it's in a downward state of nature. And similarly, that also goes for our call option, i.e. that we have two scenarios that the call option can be in, whether it's an upward state or a downward state. So the main goal is, first of all, finding a portfolio which replicates the payoff of a call option. For our portfolio, we will have two securities in that portfolio. We'll name that portfolio X, and the securities that we will be having in that portfolio at time is equal to 0 will be a bond, which has a value equal to 1 at time is equal to 0, and a stock, which has a value of the stock at time is equal to 0. Now, to illustrate how the payoff of our apologies for that. So to illustrate the payoff of our portfolio, we will have a simple matrix where capital T denotes the end point in time, where we can have either one of two payoffs. The first payoff is the payoff in the upward state of nature. However, the bond is assumed to be risk-free, so there is no impact of whether it's an upward state or a downward state on the bond's value. All that we get is simply the continuously compounded return of the bond. And for the stock, its value in the upward state will be denoted by S with an underscore U. Similarly, for the downward state will be S underscore D, and for the bond, that value does not change. And our goal is to find out how we can replicate this payoff by manipulating the weights in our portfolio. The weights will be noted as N, and we will be having N1 denoting the weight of the bond, and N2 denoting the weight of the stock. So let us resume. What we'll be doing next is basically writing this out in an equation format to solve for the ends. And so let's do that right now. So our first equation will be in the upward payoff. So in the upward payoff, we have N1 multiplied by e to the power of RT, so the weight of the bond multiplied by the payoff, plus N2, which is the weight of the stock, multiplied by the stock in the upward state of nature. And we want to set that equal to the value of the call option in the upward state of nature. As for equation 2, we would have, apologies for that, we would have the weight of the bond 1 multiplied by the payoff, which is, as I said, does not change, multiplied plus the weight of the stock multiplied by SD, and we want that downward downward situation payoff to give us the downward value of the call option. So now all we're going to do is figure out what is the value of N1 and N2 such that those two equations are true. And we will start with equation 1. So N1 would therefore equal to e to the power of negative RT multiplied by Cu minus N2 Su. So all I did over here was I moved the N2 Su to the other side, therefore there's a minus side, and then I multiplied this component with e to the power of negative RT to move basically the e to the power of RT to the other side. That's N1. So let's figure out what is N2. So to do so, we'll just simply substitute the representation of N1 in terms of N2 in equation 2 over here. So by substituting this part in here, what we simply get is that the e to the power of negative RT and e to the power of RT cancel out. So equation 2 would simply be Cu minus N2 Su plus N2 SD is equal to CD. And now we'll solve simply for N2 as we did solve for N1. And what we get is that by combining the N2s together, we get N2 is multiplied by SD. So combining those two is equal to CD minus Cu. Therefore, N2 is equal to CD. So this is the value of N2. And what we're going to do is substitute the value of N2 in the N1 representation to get the value of N1. So doing so, we will get that N1 is equal to e to the power of negative R capital T multiplied by Cu minus CD minus Cu. Okay, so we've got what the value of N1 and the value of N2 is. So our next step is to simply find the equation of the call option. So I'm just going to go to another page, but before that, I'll just simply copy those formulas over here. So remember, the whole exercise of finding n1 and n2 was basically to equate the value of our the payoff of the portfolio to the payoff of the call option. So in essence, now we have at the starting point, our portfolio would be equal to the weight of the bond multiplied by the value of the bond, which, if you remember, we set equal to 1. So simply we can get rid of that. Plus n2 multiplied by the value of the stock at the initial point in time. Time is equal to 0. And since now we found that n1 and n2, since we found the n1 and n2 that allow to have the same payoff as the call option, we can simply just substitute this to be C0. So let's begin by substituting in the values of n1 and n2 that we found. So we first have n1, just e to the power of negative r capital T multiplied by cu minus cd. I'm simply copying from over here, from the formulas that we got before. This is what n1 is. Let me just double check in case I missed something. Okay, and then we have n2, which is cd minus cu multiplied by SO. Okay, so the next step that we will do, so just to be clear, we have now solved for the value of the call option. But what I'll be attempting to do now is to manipulate this to show you a different representation of this call option equation, which will give us an insight into the concept of risk neutral pricing. So in order to do so, just bear with and I'll just manipulate the formula in order to show you that representation. So if I take e to the power of negative RT outside, therefore I would be left with So I'm taking it step by step. All I did was take e to the power of negative r capital T outside and have those both in just basically one equation or one bracket rather. And just to not change the actual formula, I just multiplied this component over here by e to the power of r capital T. So the next step that I will be doing will be to combine the common factors over here. So what I will be getting is e to the power of negative RT multiplied by Cu, and I would have plus SO. Okay, so all I did over here, the next step is combining those two parts of the equation as they have a common factor. Next, what I'll do is I will actually split this equation into two components, which is basically going to be CD multiplied by those two minus CU multiplied by those two. So I know this might not make sense right now, but all I'm doing is just changing the formula in order to get something which I already know, the representation that I already know, to show you how we arrive at that representation, which will give us an understanding once you finally see the final answer. So CU, and then we have minus CU multiplied okay. This part of the equation can be just slightly manipulated by taking CU outside as a common factor. So let's just do that in that same thing instead of wasting space. So all I'm going to do is take CU outside, and I'll be left with 1 minus that component over here. Let's write it neatly. So now what you can see is some sort of weights which are attached to CU and CD. Well, assumingly weights. Now the question is, are these weights legitimate? Do they actually sum up to equal to 1, i.e. the percentage is equal to 100? So the way that we can see that this is the case is if we think about it in terms of a market perspective, and assuming that the market has no arbitrage, then we will indeed find that this equation over here and similarly over here has to be less than 1. So the way I like to see this is by simply moving the negative sign, so basically taking a negative sign outside this small bracket and multiplying it by the numerator on the top, just to make things a bit more easy on the eyes and easy to understand at least. So let me just do this simple manipulation of taking the negative outside and putting it on top. That's possible mathematically, by the way. So we would have SU minus SD, and here we would have SU minus SO e to the power of RT. So similarly, we're just going to do the same manipulation over here just to be consistent. Now, thinking a bit about this in terms of the no arbitrage in the market, assumingly, what we notice is that SU, which is the value of the stock in the upward state of nature, has to be greater than the stock invested at the risk-free rate. So SU has to be greater than the stock simply invested at the risk-free rate. So if we get some cash and invest it at the risk-free rate, that will have to be a lesser amount that we get than simply investing in the stock market and getting SU to be in the upward state of nature. However, on the contrary side, investing at the risk-free rate also has to be better than investing in the stock, however, seeing the stock going into the downward position. Otherwise, there would be arbitrage if this is not the case, and people can make free money. I'll leave you to see how you can see that arbitrage by yourselves, but it's a very simple idea of basically you can borrow money and buy the stock or vice versa. So let's continue on. So assuming that there is no arbitrage, then SU has to be greater than SO e to the power of RT, i.e. the top component is positive, and similarly the bottom component would also be positive since SU is greater than SD. However, the spread at the bottom is larger than the spread on the top, and therefore this ratio has to be less than 1, at least. So in essence, what we have is something that is mimicking a probability because over here we have 1 minus that ratio, and over here we have that ratio, and therefore their sum has to equal to 1, or you can think of it has to equal to a weight being equal to 100%. So we've invested fully in both assets. And recall that the whole purpose is to find the value of the call option at time is equal to 0. So in essence, what we have done is we have actually found the risk neutral probabilities that of basically being in the upward state of nature and in the downward state of nature. And the reason why we call them risk neutral probabilities is because they are discounted by the risk-free rate, and if we discount it by the risk-free rate, we arrive at the value of the call option at time is equal to 0. Okay, so we found out that this is basically equal to probabilities, but not normal probabilities, but risk neutral probabilities, because we are discounting at the risk-free rate. Okay, so now we will just try to express this in a slightly more compact way. So we can say that CO is equal to the risk neutral expectation of C capital T discounted at the risk free rate. And by no arbitrage, so this is the end of finding out the value of the call option or put option. If you actually think about it, I never had any thing which forced this to be a call option. You can think of it in terms of a put option or anything. All we did was assume that we have some sort of option value which has two payoffs, and we can obviously say the same thing for a put option. So the next stage of this video is slightly a bit more related to the Black Scholes model, and I believe by looking at it through step by step, it'll give a greater understanding of what the Black Scholes model is. So this will be a part one of a series of explaining the Black Scholes in depth. So I hope you'll find it intuitive. So the next idea behind this is that if this relationship over here is true, then the following must also be true, assuming no arbitrage. And this will be a important thing later on, and when we go further into the understanding of the Black Scholes model. So let's see, why is this the case? Why do we have that if there is no arbitrage in the market, then this relationship would also follow from over here? Well, the way I like to think of it, or prove it rather, in a not so rigorous way, is by expanding the equation over here into the components of a call option. So we will assume, first of all, that the call option in the upwards and downward states has a value greater than 0. Or in other words, ST is greater than the strike price, so that the call has an actual value greater than 0. So that'll be assumption 1. And what we'll try to do next is to expand our formula over here to be equal to the payoff of the call option, but written down in so-called literal format. Okay. So since I assumed that the ST is greater than K, I won't have to have an indicator function over here, because we know that this value is always positive. So assuming that, and now what I'll do is I will we will recall the put call parity, which is basically a very important equation, which if you study derivatives at all, you will have come across it. And that formula is basically a way where we can link the prices of the calls and the puts. So the idea behind it is that if we buy a call at let's just have a timetable over here, and over here is if ST is greater than K, i.e. we are in the money, then the value of our call is st minus k. And if st is less than k, then our value of the call is going to be 0. Similarly over here, so this is a call option. And over here, if we're looking at it through the perspective of the put option, we will get the value of k minus st over here. And over here, we would get simply 0. So the idea behind it is if we have not just a put option over here, and not just a call option over here, but assuming now that we have a value which is SO, then then over here, then it's no longer going to be 0, but we will have the value of S capital T, and over here we would get plus ST from the stock, and therefore we have a value of K. And if we have K multiplied by e to the power of negative RT as a cash amount, which we invest as we go through time until maturity, and if we invest it at the continuously compounded rate, then we simply get K. And if we get K, then those will cancel out. And here, instead of being 0, we will get K. So that's simply the idea behind the put-call parity, which basically states that the call option plus the strike price, although discounted at the risk-free rate, must be equal to the value of a put option plus the value of the underlying stock. So we will now just simply interpret CO in terms of this equation. So CO would therefore be equal to PO plus SO minus K e to the power of negative RT. So now we're going to substitute this into our equation over here. So simply put PO plus SO minus K e to the power of negative RT. Okay, and this must be equal to okay, so this is what we have until now. However, now we remember our first assumption, which is that ST is greater than K. So if ST is greater than K, then the value of the put option is actually equal to 0. And now, what we would get if we move, we can move K to the other side, so we would get SO is equal to the expectation of ST. And since K is simply a strike price and it's a constant, we can take it out of the expectation. So we can have basically e to the power of negative RT, and then minus K e to the power of negative RT, and then since we move this to the other side, plus K e to the power of negative RT. And therefore, those two cancel out, and we arrive at this equation. So that's the concept of how we are. This equation interprets as that equation via no arbitrage. So one could also assume. So what would happen if ST is less than k, and that's a validated question. So what would happen then is assumption that k is less than, st is less than then we can look at it in the from the value of a put option, and we can arrive at the same exact answer of SO is equal to the expectation of ST by either having PO is equal to the expectation S of K minus ST, and substituting in the value of PO, which would be equal to CO plus K e to the power of negative R capital T minus SO. And that is the value of our put. However, since we assumed that ST is less than K, then this simply becomes 0. And we have it that this is equal to ST, and we're removing the K outside, and as well as the negative sign over here. We'll just take it outside the equation. And we would have it equal to the e to the power of negative RT plus K e to the power of negative RT. Moving the k's, basically they would cancel out, and we'd be left with negative SO is equal to negative the expectation of this. Cancel out the negative signs, and we arrive at the same equation. So that is in essence the whole concept. I hope you understood a little bit more about pricing, and this will be an intro, a very early intro towards the Black Scholes model. Thank you very much for listening.